Today our lesson is on chapter 5, energy. In here we're looking at the first one, 5.1, on basic of energies, importance of energy. Now in here, energy, this word can be found in many different kinds of things, from the battery to energy bar. And in here, energy of course is important. We can walk, talk because of it, and the plant needs the energy to grow. Now in here, our daily appliances, we see that energy works and how the vehicle moves with the energy supplying to it. In here, we got different forms of energy, so let's take a look. It exists in different forms. For example, in here, Leo wakes up because of the sound of the alarm clock. And can you say which kind of energy is involved in here? It's the sound energy, because the chemical energy that was stored not only in Leo's body but also in the alarm clock that makes the alarm clock works. In here, when he's eating a sandwich or drinking milk for breakfast, what kind of energy is involved? It involves chemical energy, because food is one form of the chemical energy that is stored in his body after he consumed the food. Then when he watch a video in class, the light energy is being supplied by the projector, and also the electricity is being transferred to the projector. And number 4, when he returned home by bus, which form of energy is being used? Is the kinetic energy, because the bus is moving. So that's why we call it kinetic energy. And number 5, when he's traveling in a lift to the upper floor, which kind of energy is involved? The potential energy. So from the lower ground floor moving up to the floor he lives in. That's why there's a potential energy involved. And number 6, when he takes a shower, the thermal energy is being consumed as it's heated the water up in the water heater. Now in here, we will look at the first kind of energy, sound energy. It's given out by object vibrating. So you see that vibrating means that something's moving. In here, the guitar is moving because of the strings, it's vibrating. That's why you can hear some sound generated by the string. And in terms, it can be turned into music. And an example is by your vocal cord. When you're singing, you will generate a sound, and you can hear that you can sing different songs with it, with your vocal cords. And that's why you can hear the different sounds is generated by you. Now in here, sound is, sometimes we can use the sound to make a refrigerator. So let's take a look. Ben and Jerry actually is an ice cream maker. They make a refrigerator out of sound.
Something very exciting is happening today. The first non-HFC coolers are entering the United States. Most people have never heard of HFCs. HFCs are man-made chemical, part of something called F-gases. F-gases are the worst greenhouse gases you've never heard of.
Well, yes, it's been a long project. I've been involved personally now for 8 years. And we've been rolling these out since 2004 in Europe and the rest of the world. So for me, it's the final step. This is the last country we moved these cabinets into. Around the world, we have now about 300,000 of these ice cream cabinets, and this is the first of, I hope, many in the US.
In 1987, Greenpeace was pushing for the banning of CFCs in the Montreal Protocol, which was successful. However, subsequent to that, chemical companies put forward the environmental alternative to CFCs, and they called HFCs environmental. Greenpeace saw immediately that HFCs were not an environmental alternative to anything.
Lots of contact points with Greenpeace, not only on refrigeration but in other issues as well. But I'd like to say that this particular issue, we've been working very closely together, and we formulated an answer really which allows us to have a win-win on both sides. So we've been working together for at least 10 years on this exercise, and we have a very good relationship with Greenpeace. So here it is, it's the hydrocarbon freezer. It looks just like any other freezer that you'll see in many of our Ben & Jerry's stores, but this is a little bit different. This cabinet not only keeps the product cold, but it does it in a way that it keeps the impact of global warming much lower.
Okay, so in here you see that the refrigerator, how it works, and there was some effort on making it into a green refrigerator. Now, in terms of the acoustic refrigerator, actually the application can be used in terms of military. So as you can tell, it's a cooling solution for the modern military operation. And people actually use that kind of refrigeration on the battlefield as of today. It has been proven effective. So in here is just some photos of what it looks like. So in here we got a thermoacoustic refrigerator. What it means is that we use a sound pitch, not any kind of sound pitch, one particular sound pitch with frequency that actually makes the sound, and then the air can be cooled by this sound. And actually the design itself is actually pretty simple. Well, you have to learn how to read the engineering drawing first. So in here I just show you a sample of what it looks like. So in here, in this object, there's the sound actually going into this motor, it's generating it, and then from that the sound created by this motor can cool off the air around it, and by cooling it off, it generates the cooling that is required by a refrigerator. So in here you see the sound can actually have a acoustic property that can be used in the refrigeration. So there are many more designs of it, I'm not going to go through that. And in the second one we have, after the sound energy, we have the chemical energy. So in here you see, in terms of chemical energy, it's usually the things we eat, the sandwich, the meal, they will generate a lot of chemical energy that can be stored in our body. And also in here you see the foods such as wood, charcoal, and petroleum itself. All these are fossil fuels, but it also can be considered as chemical energy. In here the charcoal will be burned and will give out the heat, the thermal properties of thermal energy. The battery itself has the chemical energy stored inside the battery, and it can be used in different appliances. Now before we go on to the third one, let's take a look at some of the examples we can see by looking at the chemical energy. Okay, so this one is just a quick introduction of what chemical energy is. So in here we see the examples on the things we eat, we can be processed and is safe in our body. Those are the chemical energies. So how do we measure that? In here, let's take a look at this example on what people would do.
9:46 on this Saturday morning. It's time for Imagine It, and I'm donning some really amazing wear here. Carl Nelson joins us.
All
Hi.
right. We got your fire retardant lab coat on, just in case. Mine is as well. We're going to
Okay.
talk about calories today.
All right.
Calories in food. Now, calories are not bad. They're just a measure of energy.
Okay.
And so I brought with me two different kinds of food. If you can grab a handful of toasted oats and just toss in this little porcelain bowl, we've kind of got one spectrum, one end of the spectrum of food there.
Okay.
Got some cheese puffs. We'll load that thing up.
Oh, load it up. All
We're
right.
going to load it up. What we're going to do is we're going to measure how many calories there are in each of these samples of food. Now, if we were food scientists, nutritionists, we
Sure.
would do this in a very careful and exacting way. We're going to do it really sort of down and dirty today.
No problem.
We're going
Just in the
to-
studio, right? No big deal.
Exactly. What we're going to do is we're going to burn these samples and we're going to measure or observe the flame that comes off. All right. Now, you could do that just by toasting them with the torch.
Okay.
But that's not going to be good enough. We need an excess of oxygen to get them to really combust well. And to do that, I brought with me, or I actually manufactured here, a little liquid oxygen. This blue liquid is liquid oxygen. It's about 2 balloons worth of oxygen. Far more oxygen than we need to combust this stuff. So here's the deal. I'm going to give you the torch.
Okay.
I know you're excited about
All
that.
right.
I'm going to pour the oxygen on the cereal. You're going to hit it with the torch, and then you should probably block your vision. Okay?
All right. This is going to be the end of the road for me, folks.
Go ahead and light that thing up. Don't bring it over quite yet. Get ready. All right. Bring it over and hit them. Hit it and hold there. All right.
Did I do it too soon?
No, that was great. So now you're getting a sense of how much energy there are in those
Wow.
toasted oats. They're really toasted at this
Okay.
point, right? Very, very still going. Very, very bright flame.
Yeah.
All right. Let's try it with the cheese puffs.
Okay. Now, do I need to hold it on there longer? Or a little bit less?
No, you did actually really well.
Okay.
That was pretty good. And, we don't want the smoke alarm to go off, so we'll cover that up. All right, so go ahead and light a torch again.
All right.
So this is the comparison. This is the cheese puffs. So let me get the oxygen in there. Go ahead and hit them. Hold it there for a second. Okay, pull back.
Oh, wow.
Okay, see, that's why I brought the fire extinguisher as well.
Sure.
An incredible amount of energy coming off those cheese
You
puffs.
can feel the heat from
You
that.
can feel it. You can
Yeah.
see it. I'm going to cover some of these up here.
No big deal, Carl.
All right. There's a lot of smoke here now. But, I mean,
We have insurance.
the idea, excellent. I do too. The idea here is that there's energy in the calories.
Okay.
And I'm not suggesting you eat all cheese puffs all day, but it's just a measure of energy. Okay, so the toasted oats are probably a better choice if you're going to consume just one of these two items.
Sure.
But they both have tons of energy in terms of calories.
And that's why the puffs burn longer, because they have more calories.
The puffs actually have a little bit of oil in them, so that
Okay.
helps them burn a little bit more, and they do have a few more calories. We kind of just did it really
Sure.
quickly here. We threw a handful
Not too
in.
scientific.
About 100
Right.
calories or so. But just calories, measure of energy.
Interesting. Just a reminder, folks, don't try this one at
Yeah,
home.
don't
This
try
is
this
one of
at home.
those that we'll leave to Carl and apparently me.
We do it here so they don't have to do that at home, right?
All right, Carl, well, that's awesome. And it is March. You guys have a lot of stuff.
Okay, so in here we have an example on how do we actually measuring the chemical energy. We just burn it. And of course in here we didn't do it exactly, and we need to measure it in terms of the temperature and the durations and how much energy is given out by this chemical. So in here it's just a quick example of what it would look like. Okay, now let's go to our next form of energy, the light energy. So in here, all of you have experienced that under a bright sunny day, the light is given out by the sun, and it turns into light energy for you. Now in here, some other example is the firefly also give out light. This one is the chemical ATP being used in the firefly, and of course it has to mix with oxygen to give you the light. Okay, so this one actually can be seen around the world as well in some other examples. So let's take a look at the next one. We have the lamp, we got the projector and the TV. All these use the light energy. It's converting the electrical energy into the light energy so that you can see things. And from that, let's take a look at the next one on the light energy. Has a quick introduction of what it is. Okay.
Light is the connection between us and the universe. Through light, we can experience 92,458 meters per second in a vacuum, 1 billion kilometers per hour. Electromagnetic radiation just happens to move this fast. Any particle that has no mass travels at c, without acceleration or any in between. The light that's being released from a candle does not speed up until it reaches light speed. At the very instant of its creation, its speed is c. So why is c, or the speed of light, finite then? Well, nobody knows. Our universe is just built this way. We don't have a smart answer here. So light is a part of a spectrum, an elementary particle that also behaves like a wave, propelled by two perpendicular fields traveling at the speed limit of the universe. Okay, that's nice and all, but what about all the crazy stuff about traveling at the speed of light and time, the twin paradox, quantum stuff, and things like that? We have to save them for another video. For now, let's just be happy that we evolved eyes that pick up waves of information permeating the universe, making us see things that help us to put our existence into perspective.
Okay, so in here they talk about a lot of things, and yes, they talk about the speed of light, which is this number. Okay, so in here, no, you're not going to be test you on this, no, but in here is an interesting number. So you see here, why is it this number? How come the light can travel that fast? As the video mentioned, nobody really knows, but I'm pretty sure one of you are going to find out the answer, and if you do, please let me know why. I'm wondering myself, how come the light only travel at this speed? And just in terms of this, the speed of light, c, all of you might have heard of E equal to mc squared. And E equal to mc squared, the c here is stand for this number. It's a constant, it doesn't change. Why does the energy is related to this in terms of how fast you can move? Well, even Albert Einstein don't really have an answer for that. So it's up to you to find out how come we have this number here. And for that, I do not have an answer to that. Okay, so in here, but we can capture this light energy. How do we do that? We're using solar cells. And in here, we just a quick introduction on how does a solar cell works. And let's take a look.
You probably know that plants get their energy from the sun through their leaves in a process called photosynthesis. We humans don't have our own leaves, but maybe we can get energy from the sun in a different way. Electrical energy, that is. Could there be some kind of electrical leaf? A solar cell gathers light from the sun and generates electricity, just as a leaf generates food for a plant. Let's find out how. The sun emits energy in the form of waves. These waves can range in length from short ultraviolet waves through the rainbow of the visible spectrum to long infrared waves. When the sun is shining, these waves move towards the Earth and hit the surface of solar cells. Let's take a closer look. The active part of a solar cell is a wafer made of semiconductive material, typically silicon. A semiconductor is a type of material that normally doesn't conduct electricity well, but it can be made more conductive under certain conditions. The semiconductor part of the solar cell has 3 layers. The thin top layer contains silicon and a very tiny amount of an element such as phosphorus that has more electrons than silicon. This gives the top layer an excess of electrons that are free to move and make the material more conductive. The top layer is also called negative type or N-type, as it favors the collection and transport of electrons. The thin bottom layer contains both silicon and an element such as boron that has fewer electrons than silicon. This gives the bottom layer fewer electrons that are free to move, therefore making the material less conductive for electrons. A missing electron can be described as an effective positive charge. Therefore, the bottom layer is called positive type, or p-type, as it preferentially favors the collection and transport of these positive charges, also dubbed holes. The thicker middle layer has only slightly fewer electrons, making it marginally p-type. Thin metal lines, typically made of silver, are printed on top n-type layer, and the bottom p-type layer is in contact with an aluminum plate. When light waves hit the top surface of the silicon solar cell, only light with wavelengths from a specific window of the solar spectrum, 350 to 1140 nanometers, are absorbed into the middle layer of the solar cell. This range of wavelengths includes the visible spectrum. Ultraviolet wavelengths are so short they stop at the surface, and infrared wavelengths are so long they can't be absorbed and pass right through the cell or are reflected back. The light wave knocks an electron off a silicon atom, setting the electron loose and leaving an area of positive charge, a hole, where the electron used to be. The loose electron then moves towards the top and reaches the top n-type layer, which readily accepts electrons. Similarly, the loose hole moves towards the bottom and reaches the bottom p-type layer, which readily accepts holes. This continues as long as sunlight shines on the solar cell. Now that the electrons and the holes have been separated, connecting a wire between the top and the bottom metal electrodes provides a pathway for the electrons to move towards the holes. Flow of electrons is electrical current. One solar cell produces several watts of power. This may be sufficient for running a calculator or a phone charger, but it's not sufficient for running a toaster, for example, which uses 1,000 watts. So, several solar cells, typically 32, are wired together to make a solar panel. Several solar panels are needed to generate enough electricity to power a household. As leaves generate food for plants directly from the sun's rays, solar cells are a viable way to convert the sun's rays directly into electricity that we can use. Future challenges include improving the efficiency by which a solar cell converts sunlight to electricity and making the solar energy cheaper. Of course, solar cells produce electricity only during the day, so storing the electricity efficiently for use during nighttime is another important challenge. Advancements in solar technology present the potential to power our lives if we just leave it to the sun.
Okay, so in here it talks about how we're going to capture this light energy, and in here we're doing it not really effectively or efficiently for that matter. So in here we are improving, and one of the biggest country that produce a lot of this solar cell is China. So in here we actually have an advantage of getting the latest solar cell manufacturer by China itself. Okay, so it's number 3, and in here we see that the light can help us to see things, and we come to the last one for today's lesson is the thermal energy. In here, sun also give out this thermal energy. Let's take a look. In here, all the appliances, the iron, the heater, the stove, all give out thermal energy. And it's one of those things that you can feel it, and you can actually feel what the temperature difference is. So the hotter an object, the more thermal energy it gives out. Now, in here you have to be careful. You should not think that only hot energy would give thermal energy. In fact, a really cold temperature, as long as there is some temperature, it will give out the thermal energy. Even just a normal room temperature glass of water, it will still give out thermal energy. If you put it inside a refrigerator, the thermal energy given out by the glass of water will go into the refrigerator. And when you give out all the thermal energy, a lot of it, it will start to freeze into ice. So in here, not only hot object would give out energy, but also the cold objects can still give out thermal energy. So is there everything that can give out thermal energy? Let's take a look. Now, in here, as I mentioned to most of my classes, we got a concept of absolute zero. What temperature is that? Is minus 273 degrees. Okay, so what does it do? So in here, we got the minus 273 degrees. In theory, if any object or particles reaches that temperature of minus 273 degrees, it will stop giving out any energy. So only at that temperature I can tell you for sure, okay, there is no thermal energy giving out by that particle at this temperature. Now, in here, let's take a look at what does Bill have to say about the thermal energy.
Bill Nye the Science Guy. Bill Nye the Science. Bill Nye the Science Guy.
The mountains are icy, but they've got motion of molecules. Ha! See, even cold things have heat. Things like snow and icy mountain lakes and glaciers. They've got heat. Anything with molecules has heat. It's just that the molecules in cold things are moving more slowly than the molecules in warm things. You with me? Here's a question. Which has more heat energy? This hot burning match or this beautiful ice sculpture of science? Well, the match is hot, right? The sculpture's cold. Well, they're both made of molecules, right? But which has more molecules? Well, the ice sculpture. A lot more molecules. So although they're much colder than the match, they actually have more heat energy. More molecules, more heat energy. Think of it this way. Suppose you tried to take a burning match and use it to melt the whole ice sculpture. It's not going to happen, right? I mean, the match is going to run out of molecules long before the sculpture. So, more molecules, more heat energy. Ow! Ow!
Careful. Bill Nye the Science Guy.
Okay, so in here, that's today's lesson on 4 different types of energy. So the first one, remember what that is? The sun energy, okay? That's what we talk about, the sun energy, that's the first one. And then the second one is the chemical energy, the foods we eat, and it can be stored in our body. And then the third one is the light energy. In here, the light energy. We mentioned about a lot of light property. For example, the speed of how fast it goes, and how we're going to capture that with the solar panel. So in here, the third one is light energy, and of course, the last one we have just talked about is by Bill is the thermal energy, the heat energy, the ability you sense the temperature difference. That is the thermal energy. So today our lesson will be these 4 different types of energy. In our next lesson, we will talk about the remaining types of energy. And that's the end of today's lesson.